So let's get started for radiation effects. So we'll be more talking about single event effects. In the last lectures, we talked about total ionizing dose effects, right? So these are the two main circuit response for memory circuit under radiation. So total dose effects is more like a cumulative parametric degradation, whereas single event effect is it's a transient probabilistic event. So either a bit will be flipped or it will not. It is nothing to do with cumulative, right? It's a very stochastic event under a radiation environment. Typically, SRAM, DRAM, those volatile memories are more susceptible to this kind of single event effect. And we'll talk about the physics of single event effect, more specifically, these three charge terms. There is a charge deposited because of heavy ion passing through your device. How much charge is deposited? We'll talk about with equations. Then how much charge is collected by the device, because most of the time we are talking about MOSFET, right? So MOSFET will collect this charge that is deposited by heavy ion passing through it. And then very critical concept is called critical charge, that how much charge you need to upset a bit. So this is the critical charge. So we'll talk about all those terms, and then we will see the case studies of say single event effects on DRAM as well as SRAM, and then we'll define the soft error rate. Okay, so to get started with, what is meant by single event phenomena, right? So I think we talked in the last class that single event effect or single event phenomena happens when a heavy ion pass through a PN junction. So this is your PN junction. Green is your N plus region. This purple is your P region. So whenever an ion pass through it, right, along its path, it ionizes the material. It creates electron and hole pair. Now, why PN junction is critical? Because PN junction offers an electric field even if there is no voltage anywhere, right? So think about a solar cell, right? Suppose you have not given any voltage. Solar cell produces this voltage because of ionization. So similarly here, when an ion passes through this PN junction, it creates electron hole pair. But because PN junction has this inbuilt electric field, right? Electrons will go to this opposite to the field direction, and holes will go in along the direction of field direction. So in this picture, which is the electric field direction? Top or bottom? Bottom is the field direction. So electrons will move towards the N plus region and holes will go to this P region. The reason is what type of ions you have, right? So N has donor ions which are positive, and P has acceptor ions which are negative. So always electric field is from positive ion to negative ion. So electric field direction is down. So that means electrons will be collected top, holes will be collected in the bottom, okay? Or in other words, you can say, which is N plus region, and N plus region will collect electrons, P plus region will collect holes. So after ion pass through it, okay? So that's the single event phenomena. And this is very much a random event, right? So even in terrestrial, as I said in the last class, even in terrestrial, single event can take place. For example, in a flight, for example, even in your memory packaging material may have radioactive element, and those radioactive element can also cause single event upset in the underlying memory array. Okay, so now the circuit response of single event phenomena is called single event effect, right? So, and it can cause two types of errors. One is called soft error. Soft error means an error which is correctable, right? So you have stored in DRAM, for example, 1. This 1 has flipped to 0, but that doesn't cause any hard failure in the memory circuits. So there are two types of error. One is called soft error, which is correctable. If you turn it off, turn it on again, error goes away, or if you refresh the data, error goes away, right? So those are the soft error. And there is a hard error, right? Hard error is more like a permanent damage. That means the radiation induced error cannot be corrected by the circuit, right? Even if you turn off, turn on, the error doesn't go away. right? It can be stuck at 1 error, stuck at 0, right? You cannot stuck back, you cannot write it back, for example, the bit error. Or it can be more damaging effects like latch up, burnout. Those are like heavy, lot of current goes through it. It is causing some burning out of the circuit. So those kind of errors are also called hard errors. So typically these are the two types of errors caused by single event effects. Now let's understand the physics of single event effect, right? So how charge is generated, what are the steps, what are the chronological steps happens. By chronological, I mean in picosecond time scale. So at the first step is an ion passing through a p-n junction. And the ion will be creating electron-hole pair along its path, right, as it passes through the material. So it deposits its energy in the form of ionization. So this is a very good paper. I mean, this is from Robert Bauman from TI. He was working in TI that time. So I took some of those pictures from his paper. So this is the first step. Second step, collection will start because the ion will zip through, right? It will go through in less than a femtosecond maybe. Now after that, the effects will start. So after that, this p-n junction effect will start. You see electrons are now all going to the n+ region. These are all electron. Initially, electron hole are mixed. Why electrons are funneled through it? Because of electric field. Because of this p-n junction effect, right? The electric field will streamline all those electrons that has been generated by this ion track towards the end region. And the holes, all the remaining holes will be now kind of collected by the silicon substrate, right? So that is the second step, which is the drift phase. Drift is electric field dominated, and you can see your p-n junction is expanded because of this heavy ion related effect. And then, so p-n junction is expanded because locally, right, because of these holes, you get local potential, right? So your p-n junction depends on what is so like reverse bias. You are with those holes, they are creating it's more like a reverse bias junction. So that's why junction is expanded or your collection area is increased. And then at the later time scale, say hundreds of picosecond, in that time scale, there will be diffusion taking place. So diffusion will take over the last phase of start. So if you plot it, all these three phases, this is the onset of the event. That means ion just passed through it. X-axis time is, 10 to the minus 12 means picosecond, right? So from 1 picosecond to within a nanosecond, right? All these things will happen. So at the very beginning, you have a prompt charge collection. That's why you see this peak. This is the drift phase. And then this state is more like diffusion dominated, what we talked about here. The electron and hole will diffuse. Diffusion means a little bit slow, right? Less carriers are left. So these are the three phases of event. And if we integrate this curve, right, this is y-axis is the current, x-axis is the time. So if you integrate this curve, you can get what is the total charge collected by the device after the event. Event means single event effect. So this is all the physics that you need to know, how it happens. Everything happens in picosecond. Now the question is whether this current can cause a burnout event, right? Or the amount of charge deposited, can it be enough to flip a DRAM bit? Because those currents will either charge a capacitor or discharge a capacitor. If you think about an SRAM node, right? SRAM node has Q equal to 1 or Q bar equal to 1. One of the floating node is 1. So if this current can discharge that node, then you can see an upset. If this current is not enough to discharge a node, then you will not see an upset. All this event will take place, but you will not see an upset, right? So that's why it's called soft error. So once upset happens, then especially in SRAM and all where error correction is less, right? The error correction mechanism is less. For example, think about FPGA bit stream, right? One bit got flipped because of this effect, then entire your program will not work. Entire your memory configuration file will be changed, right? One bit error. So we gave few examples in the last class. For example, the voting machine, that one bit flips because of this soft error can cause your voting outcome because the bit position matters, why this bit got flipped. Okay, so we'll deep dive all these effects and we'll connect all those phenomena with the bit error rate of SRAM and DRAM as you go forward. You can ask me questions as you go forward, right? Anytime if you think more explanation needed. The question is which junction, right? So you in a MOSFET there are two junctions, source and drain. Which junction is more vulnerable for this single event effect or single event phenomena? And why? What do you think? Suppose an ion can go through source junction, right? This PN junction, versus an ion can go through this PN junction. Which one you think will be more? Yes.
Drain.
Yes, drain is typically more because why?
It's not next to the ground.
Yeah, so typically drain is connected to the high voltage, right? Like this, here. So that means drain is reverse bias, right? So reverse bias junction will collect more charge with more field. Reverse bias means there is more field, depletion region is wide. So more depletion region means more electric field or more area, charge collection area is large. Whereas a MOSFET, right, if it is in off state, in off state both will be grounded, source and drain. In that case, both source and drain will be equally likely. Both can collect same amount of charge, whatever ion goes through it. But typically source is never reverse bias, right? Source is grounded in a circuit. So in a typical scenario, this will be the case. When a MOSFET is on, then drain will be more vulnerable junction. When it is off, both are equally likely in terms of charge collection. Just because of PN junction effect, right? You want reverse bias. Reverse bias means more electric field, more collection area of the junction. So all this thickness will matter, and we'll solve few problems that how much thick will result in how much picocoulomb you will collect. Okay, so that's, I hope this makes sense, that your collection, right? Collection depends on biasing or reverse biasing of the junction. Typically, drain junction is reverse bias more because you give positive voltage on the drain. There is a reverse bias condition for this drain and substrate junction. So that means after ion pass through it, right, all these electrons, this green, will go through this drain region. So in terms of current, it is actually going in, sinking into this drain, right? Because electron flow is opposite to the current flow. That means if you connect a DRAM capacitor here, and this DRAM capacitor is charged, this will discharge because of this radiation effect. Because this electron will go to this capacitor and will neutralize the charge stored in the capacitor. Okay, so that's the access transistor, right? So access transistor is MOSFET, typical MOSFET. So that's how radiation can affect your memory circuit. Now, these three charges, right, we talked about is more critical to understand. To give you a mathematical background for soft error, we need to understand these three charges. One is the deposited charge, how much charge an ion can deposit. So that depends on at what angle the ion is coming. If it is coming perpendicular versus if it's coming at an angle, which is more dangerous or which has more charge deposition capability?
At an angle.
At an angle, because path length will be large, right? Because look here, if it comes at vertical, right? If theta is 0, for example, right? It comes normal incidence, then just the thickness. Thickness is your ion track. Whereas if it comes to an angle, say 30 degree, 40 degree, then by cos theta, right, that angle, you can expand or you can elongate the path length. More path length means more charge deposition, because along the path you ionize the material. Yeah. So this is one thing, and the quantification, right, is of this ion, right, in terms of its energy and all, or how much charge deposition capability that ion has. We quantify it with linear energy transfer. Okay. So along its path, how many electron hole pair will be generated? That is the more critical thing from memory circuit point of view, right? From semiconductor point of view, we need to understand that, okay, an ion with some energy, mega electron volt, for example, is passing through it. Then how can I know what is the charge deposited? So this LET of the ion, we have to know LET has the unit mega electron volt centimeter square per milligram. That means it normalizes by the density of the material, right? So for example, if you multiply the LET of the ion with density of the material, like silicon has one density, right? Silicon as crystal. Silicon dioxide will have different density. So density will give you energy deposition in mega electron volt per centimeter, right? So That means if you know the LET, you can use it for any material with corresponding density, then you will get this energy deposition. And from this energy deposition, you can find out how many electron hole pairs will be generated. For example, if you look at this equation, right? So this equation, you can plug in LET value, you plug in the density. Rho is the density of the material. And this cos theta is coming because of path length, right? So if you use this equation, you can find what is the charge deposited, because that is what, as an electrical engineering point of view, we are interested in. Because of ion passing through this material, what is your Qi? So all you need to know what is the LET of the ion, right? What is the linear energy transfer for the ion. For example, if you look at silicon, its ionization pair constant, right? That 3.6 electron volt you need to ionize. So from that you can find it out how many electron hole pair will be generated when an ion with certain LET goes through the silicon. So if you plug in the density of silicon here, rho silicon EP as 3.6, you get, this is the number. So for this course, right, silicon is the material of choice, because all this mainstream memory, SRAM, DRAM, flash, they're all made of silicon. So instead of this equation, you can look at this equation. So this equation just says this LET times 0.01. That means if your particular LET is 100 MeV, right, you are depositing 1 picocoulomb per micron. So this Qi is expressed in picocoulomb per micron. Then this is a very simple relationship that you can use, right? So whatever the LET of the ion passing through this silicon, you just multiply with 0.01 to find out how many picocoulomb you are depositing in the material. Suppose your material thickness, silicon substrate, right? Silicon wafer is 1 micron thick, suppose your your MOSFET device. So then if you have 100 MeV is your LET of the ion, then you will get 1 picocoulomb deposited. Now, second question we will ask, is 1 picocoulomb enough to flip a bit? Okay, so this is the sum of those equations then you need to use to find out what is the total charge deposited and whether that deposited charge is enough to upset a bit. Any question on charge deposition part? Okay, so I think this is a simplified equation. This is a more generic equation. Any material you take, you plug in its density, you plug in the ionization constant, EP. EP for silicon is 3.6 electron volt. That means yeah.
So that simplified is only for silicon?
So this equation is only for silicon, this 0.01. This is for everyone. Yeah, this is general.
So this is your name.
Theta is equal. Yeah. So this here you assume theta equal to 0, normal incidence. But yeah, this is a good question. I think in homework you'll be tested. There will be angle will be given to you. So based on angle, you just divide by cos theta basically. So cos 0 is 1. So this is the least amount. But if you come with a certain angle, you can deposit more charge. Okay, so next is the collection. So this is the deposited is the maximum that you can collect. Not everyone, so suppose you deposit 100 electron hole pair, right? Not all these 100 electrons will be collected. Some will be recombining, because in a semiconductor material, generation and recombination always takes place, right? So how much you will collect depends on what is the electric field or what is the junction of this device, right? For example, if this is the ion going through it, right? First, you can see this electron will move, right? Electron cannot move more than speed of light, for example, right? But much lower than, it's called saturation velocity. Electron has the saturation velocity as a function of electric field, right? So this is 10 to the power 7. So this is the highest speed electron can have in silicon. So this is the saturation velocity, and if you multiply with this thickness, so suppose your substrate thickness is 0.5 micron, you can find it out how long electron will take to get collected. So around 5 picosecond, right? So distance divided by speed will give you time. So this is the time scale we are talking about. In a couple of picoseconds, all the deposited charge will be collected. Either electron in one terminal, holes in the substrate terminal typically. Electron in the N plus source or N plus drain terminal. And these are the different mechanism for collection of charge: drift, and then funneling, then diffusion. So all those mechanisms will take place, and the three charge collection mechanism, and overall the total collected charge over time will be your drift charge, diffusion, your funneling charge, and your diffusion charge. So drift is within this PN junction, funneling is the PN junction expansion, and then diffusion means farther away from the PN junction. Charge can also be collected through diffusion mechanism. Okay, and from mathematical point of view, you can say that this ion strike, we can model it with a current source. A current source is more like a delta function, right? Which is more like a spike. A very small amount of time, you see a sudden current spike, and that magnitude of the spike will depend on how much charge you have collected. Then the last thing, so this is all about charge collection. We talked about charge deposition, and ion goes through it depending on the energy of the ion, depending on the LET of the ion, depending on the ion path, how long the ion took, right, to cross this PN junction. So we can find what is the charge deposition, and charge collection depends on the field profile, PN junction profile. And finally, the critical charge. The critical charge is defined as the minimum charge, right, that is needed to upset a bit. So it depends on the logic state, right? For example, SRAM versus DRAM can have very different critical charge. But in general, you can think about what is the charge, right, when you store an information. So it depends on the capacitance of that node and the supply voltage. So this is more like a rough calculation. So what do you think, if for a lower technology node versus a higher technology node, which one will have higher critical charge, or how this critical charge depends on technology node?
Smaller will have lower critical charge.
Yeah, so pretty much straightforward, right? As you go to the small technology node, your capacitance decreases, because capacitance is proportional to area, right? And supply voltage also actually goes down as you go to the lower technology node. That means your charge to upset a bit can be very, very small. Can be 1 picocoulomb or less than maybe 100 femtocoulomb will be good enough to upset a bit. So yeah, so that's why this is a serious issue for ultra scale devices. We are scaling, right? Scaling is the workhorse for semiconductor industry. You are increasing the bit density, but you are making it more and more sensitive because your critical charge is going down. But the story is not simple, because what matters is your collected charge, right? Should be more than critical charge. Yes, your critical charge is going down, but what if your collected charge is also going down? Because collected charge depends on the thickness of the material. So as you make areas small, if you are also thinning down the substrate and all, then your collected charge can also go down. So the fundamental condition for causing an upset is whatever charge you have collected, that should be more than the critical charge. Not just making things small doesn't mean that it is becoming more and more sensitive to radiation. Okay, if your collected charge also goes down because of scaling, then you are fine. So we have to see this condition, whether this condition is, if this condition is satisfied, then you will see a memory upset. Questions? Anything? Okay. So this plot actually talks about with scaling, which is feature size going down less than a micron, your critical charge is going down. So that is fine, that is understandable, because as you scale the device, your area capacitance of the storage node is decreasing. Right? It can be a DRAM capacitor or the SRAM floating node, right? This capacitance is decreasing, the VDD is also decreasing, so your critical charge is going down. But at the same time, we will see this collected charge also goes down as we make things small. So let's look at few specific examples. For example, we'll talk about first DRAM upset mechanism condition in more detail, and then we talked about SRAM, and finally we'll conclude. So this is your DRAM cell, 1T, 1C. That's what we talked about in this course. Now, first you identify what are the sensitive nodes for the DRAM. For example, there is one PN junction at the source side, right? This is the source, the arrow. Another PN junction is at the drain side, right? So this is your word line, row, column is connected to a bit line, and bit line is connected to the drain of this NMOS transistor, which is the access transistor. So radiation effects on this access transistor actually is critical, because this access transistor, when it hit by a ion passing through it, right, like this, only then you can create a current. For example, if radiation goes through this gate directly, it doesn't create any current. There is no PN junction along the gate. Make sense? So this is the important thing to understand for single event effect, that ion should pass through a PN junction, and that PN junction will then create a transient current, right? For example, if ion pass through this source junction here, then only source junction means which will come out of the transistor, electron will come out or holes will come out. So that's why you need to understand NMOS versus PMOS, right? So here we're talking about NMOS access transistor. In DRAM, access transistors are NMOS, right? All the time, because you charge it, you discharge it. So now if access transistor is NMOS, that means source is NMOS. That means electrons will come out after radiation strike, right? So if electron comes out, it will discharge this capacitor basically. Okay, electron coming out means current is going into the MOSFET. So that means this charge that is stored in this is going to the MOSFET, and will it go to bit line or will it go to ground? That charge. What is the path of this charge? So the path of the charge is, it is going to be ground, right? Because this is the path. This junction, this P region is the substrate. The substrate is connected to the ground body, right? So nothing will happen, nothing will go to this bit line. Okay, so this is the one important thing, that okay, current will spike up whenever there is a voltage, there is a ion going through it, and as a result, this capacitor voltage will go down. Because capacitor is storing charge, right? It will go down. So that's how you use an upset, right? So it is very, in picosecond it will happen, right? So it's refresh is millisecond range. So by this time it will be upset. If a DRAM cell is hit by an ion, right, at this appropriate junction, it will cause an upset. So 1 to 0. Can 0 to 1 can happen or no? Is there a possibility? Anyone? You don't say any possibility. So 1 to 0 we understood. This capacitor will charge, will discharge. And in an N junction, always electrons will come out or nothing will come out. Holes will never come out. So through this, no, only 1 to 0. But through this bit line side, it can happen. Because if you look at here, right, strike at the source, yes, it will discharge the storage capacitor. But strike at the drain will discharge this bit line precharge voltage. Suppose you are sensing, right, just before sensing, strike happens. Then there can be an error. So this is much less likely or possible that 0 to 1. 0 to 1 is not because of capacitor getting charged. It is because precharge voltage of the bit line can be messed up. Okay, so you precharge that bit line to VDD by 2 and see whether it is discharging or not. So that can happen through this this strike also. But predominantly it is 1 to 0 error. Okay, so let's look at the steps. So this is your DRAM cell. This is your 1T, 1C. 1T means one transistor, one capacitor cell. Suppose your supply voltage is VDD and capacitor storage node capacitor is C, then storage charge is QS. Now a strike happens like this. If a strike happens and it passes through this PN junction, then electron will be deposited on the capacitor, or in other words, capacitor will discharge through this NMOS transistor to the ground, right? So electron hole pairs, electron is collected, and as a result, this capacitor, which was initially charged, can become discharged, right? So all you need to know, what is the collected charge and what is my storage charge, or what is the critical charge. What is the critical charge to upset a DRAM? Is it CVDD, half CVDD? What is that value? Half, right? Because your sensing margin is there, right? CVDD or maximum charge on the capacitor. You can still sense till it is half CVDD. After that, there will be flip. So that's why you need to understand this noise margin. So typically you keep a V noise margin, right? So how much voltage loss you can tolerate in a DRAM, because in DRAM always leakage happens, right? So you refresh it after some time, and that refresh interval defines what is the noise margin. And if you're upset, right, if your collector charge is more than this noise margin, then you will see bit is flipped, or 1 will be read as 0. Or more mathematically, you can define this equation is like this. So what is the change in the node voltage? Node voltage change because of the collector charge divided by node capacitance. Q equal to CV, right? That's the one main equation we learned in this course. Not in this course, in school. So okay, so this collected charge divided by node of the capacitance will change, will cause the amount of voltage shift. And if you have critical charge will be noise margin times the capacitance. So if this critical charge is lower than collected charge, you will see an upset. So that's the condition of an upset for DRAM. Okay, so let's look at the upset thing. So we talked about DRAM cell. Sensitive node is more like source junction. If ion goes through the source junction, a charged capacitor will get discharged, and you can model this charging effect with a current source, right? Because this current source, it will tell you how much charge is being collected. And if this collection is less than, if the collected charge is more than your equivalent noise margin, you will see an upset. So let's solve one problem and then we'll move on. Okay, so here we are assuming normal incidence. The first step is estimate the deposited charge, right? So deposited charge depends on the thickness of the substrate. It's 2 nanometers thick, and LET is 5 MeV. So 5 MeV times 0.01 will give you picocoulomb per micron. So what is the deposited charge? You don't need calculator, just multiply. If you know, so LET is, so here Q deposited is the LET times 0.01, right? Picocoulomb per micrometer. So deposited per unit length. What is the total charge deposited? You have to multiply by length, right? So Q deposited total will be thickness of the device, P silicon, times this one, right? LED is 5 MeV, so 5 times 0.01 picocoulomb. This is the unit. So 0.1, right? 0.1 picocoulomb. Make sense? The thickness is 2 and 0.01. So 0.1 picocoulomb will be deposited. Now is 0.1 good enough to upset this DRAM cell? So that's where the second part comes in. Estimate the critical charge for upset, right? Assume storage node capacitance is 50 femtofarad and noise margin is 2.5 volt, which is half the VDD. And then find out if there is an upset will happen or not. Will there be single event upset if all the deposited charge is collected? Suppose you're assuming, right, the maximum you can collect, whatever is deposited. And what will be the voltage across the storage capacitor just after the strike? So that depends on how much charge you lost. So those are the questions, these are the type of questions you expect, for example, in radiation effects on memory. So your deposited charge is 0.1 picocoulomb, as we said, is the thickness times deposited charge per unit length. So the symbols, maybe QI, I will be using for deposited charge per unit length. Total deposited charge, we just write Q deposit, which is 0.1 picocoulomb. And then critical charge is C, capacitance, femtofarad times voltage, which comes around 0.125 picocoulomb. What do you think? Will there be upset or no upset? No upset if you read immediately after strike. Right, you are already at a lower charge picosecond, but you will be reading maybe after, you will be refreshing. So it depends, it all depends. So just after strike, you can say there is no upset. So under that assumption. So it depends on when strike is happening. If strike is happening just before refresh, then no upset. Or it also depends on the initial condition of the capacitor. So this detailed actual thing is a little complex, but for problem solving, we will make some simplistic assumption. Okay, you are reading just after strike, or just after strike, will there be any upset? Answer here is, with this, you can say no upset. Then what is the voltage? Voltage across the capacitor. Initially, voltage was 5. Capacitor was fully charged. But now, capacitor has lost 0.1 picocoulomb. What is the voltage, right? Will it be more than 2.5? Less than 2.5? Should be more than 2.5, right? Because there is no upset. If it was less than 2.5, from 5, if it goes below 2.5, there will be upset. But we concluded, right? There is no upset. So we can find what is the voltage. Voltage delta V is 2 volt. So that means change in voltage across the capacitor is collected charge divided by node capacitance. So you collected is 0.1 picocoulomb divided by node capacitance. So 2 volt drop because of this deposited charge. That means your final voltage is 3 volt. So you're very close to the upset. That means if you don't refresh it soon enough, maybe it can cause error. Makes sense, this simple calculation, but this simple calculation is insightful. You know how to correlate LET of the ion, which is the unit for heavy ion energy, and the deposited charge and collected charge. Any questions so far? Okay, so now let's move to SRAM. SRAM is even interesting, more interesting, I'll say. So, because there is a restoring mechanism in SRAM. In DRAM, there is no restoring mechanism, right? So that means DRAM is more vulnerable to upsets. Whereas in SRAM, you can restore. Yes, you can lose some charge, but immediately PMOS can come in. For example, here, if you look at this SRAM cell, it is holding 0. This is your Q node, which is holding 0, right? And Q bar is holding 1. This is the state during the hold position. Now tell me which junctions are critical. Because if this PMOS is hit, this NMOS is hit, not maybe everybody will be upsetting this cell. So that's why you need to understand the charge dynamics. When an NMOS transistor is hit by an ion, electrons comes out from this source or drain, right? Doesn't matter, because N will collect electron. When a PMOS is hit by an ion, holes comes out. With this is the cartoon, right, that we talked about. If an NMOS, this is an NMOS. NMOS hit by an ion, electrons comes out. Right? That means it will discharge any capacitor at that node. If a PMOS is hit, holes will come out. That means it will charge the capacitor. With this thing, you tell me what are the critical junctions. Name those junctions, or which transistor should be hit.
A2 source.
A2 source, yes, that is one. There are more. Anything else? A2 source is the correct answer, because if this node is hit, right, this will discharge this capacitor. Not through the bit line, through this ground substrate. What else you can see?
P1.
P1? Yes, answer is correct. P1, this junction, drain. Because for P, this is their source, this is your drain. Where current enters, this is the source, right? This is the angle. So this is your drain. So P1 drain is another critical junction. There is one more. N2 drain. Right. So this junction will discharge this Q. This junction will discharge this Q, and only this junction will charge this Q. So these are the three critical junctions. Drain of N2, drain of P1, because P1 will charge, right? If this node gets charged because of the strike, then also there is an upset. Upset can take place. And third is drain of A2. So these are the three critical junctions. So in multiple choice questions, these are the things that are also included in midterm, right? Yes, there will not be any descriptive problem, but you can be asked, okay, the P2 is hit by ion when it is holding Q equal to 0. Will there be any upset? Answer should be no, because P2 has nothing to do with upset here. Only these three are the important junction which can cause upset. So yeah, so this is all probabilistic event, but still it happens, right? When things wants to go wrong, it will go wrong. So when you send something in spacecraft, any of the junction can be hit, and you will see a soft error in your FPGA board or in your SRAM cells. So this location dependence is very important to understand for SRAM, because SRAM has many junctions around. For DRAM, this is very simple, one access transistor. But for SRAM, there are multiple. So you need to understand that which node is depositing charge, or which node is discharging this capacitor and all. So this is the thumb rule. Particle strike at NMOS causes current flow into the transistor, discharging the corresponding output node, right? Because NMOS will eject electrons. Electrons will come out, or in other words, it will sink whatever the charged node. And particle strike at PMOS causes current flow out of the transistor, charging the corresponding output node. So that's the simple picture. NMOS versus PMOS. NMOS, it will deposit electrons, or it will sink current. PMOS, it will deposit holes, or it will source the current, or charge, right? Yeah, so this is how a charge. So any particle strike we will model with a current source. That means this current source for NMOS will sink this charged node capacitor. Now there is an important role for timing. Now, how long, right? So yes, you have deposited some charge, but if because of this positive feedback, this charge can be restored, that means how long, right, it remains low. That is important. So for example, suppose this is your Q and this is your Q bar, VA and VB, right? So this is your SRAM cell storage node. If this node is affected, there will be some time delay to reach. Suppose this capacitor is discharged, right? This is one, but because of radiation strike, this capacitor is discharged. Now there has to be some time delay to propagate this effect from here to here, and then the latch will be locked. But within this propagation delay, if this capacitor gets recharged again by this PMOS, then you will not see any upset. Make sense? So this radiation will take place in a femtosecond, right? Particle will go through it. Now, how long that effect remains depends on this PMOS transistor. That what is the strength of those PMOS transistor? It also depends on how long this propagation delay for individual inverter is. So, what do you think? Longer propagation delay will help, or shorter propagation delay will help?
Longer will see less.
Yes, longer will see less disturb. That's correct, because if B takes longer time, right? Suppose 10 nanosecond it takes, right? 10 nanosecond is maybe large, maybe say 5 nanosecond it takes. Then this node got 5 nanosecond time to get recharged again, right? Because radiation will hit and it will discharge this capacitor. Now you have 5 nanosecond, right? For this capacitor to be charged by the PMOS. Because PMOS wants to replenish that charge, right? That's the whole point of static SRAM. There is nothing charging mechanism in DRAM, right? So that's why DRAM is more sensitive. But let's understand this propagation delay a little bit more. But I hope you understood. If propagation delay is large, which is bad, right? We don't want to design an SRAM cell with longer propagation delay. Then I cannot access. Your access time and everything will be small. But that's the compromise. If you want to make it red hard, you want to design your inverter with a longer delay, right? So that's the compromise or trade-off. There's been fast SRAM. If you design it for very fast SRAM, it has a more sensitivity to soft error. Okay, so that's what we are talking about. When this is discharged, this PMOS, right? This PMOS wants to charge this capacitor. Yes, this NMOS is hit by ion, and this NMOS will discharge this capacitor very soon, within 1 or 2 picosecond. Within 1 or 2 picosecond, this capacitor is gone to zero, right? Charge zero. But there's a propagation delay, TPD. Within this propagation delay, this PMOS can come to rescue, can keep charging this capacitor. And if that charging is good enough, right? If this propagation delay is long enough, then by the time this effect goes here, this has been charged, and then it will not be upset. Okay, so let's look at this role of timing for SRAM upset. So just after strike, the node which got strike goes down, right? VA, if this is Q equal to 1 node, that voltage will go down. And that will happen in a very short time scale, maximum 10 picosecond, right? Within a picosecond, it will happen. The PMOS starts to restore the node. PMOS job is, if a charge is, because this is on PMOS, right? Any charge is gone, this PMOS will replenish that charge. If the inverter propagation delay is large, no offset will take place. Or more analytically, you can look at it like this. So your strike happens here, this vertical line. Before strike happens, the node was charged to VDD. So Q equal to 1. So the node voltage is VDD. The moment strike happens, immediately this node voltage will go down. And it can go to negative also, right? Depending on how much is your deposited charge. If your deposited or if your collected charge is more than the critical charge or more than the stored charge, then the voltage can be negative as well at that particular node, right? But it will keep rising. The more you allow time, right? So that's where the propagation delay of this other inverter comes in. Then it will rise to again VA, and as if nothing has happened. So if propagation delay is long, then this node will go back and there will be no upset. But if propagation delay is low, right? If this window is low, then it has not got enough time to reach. So then VB, right, which is the other node. This is VA, this is VB, or Q bar. So Q bar will then, in that case, will rise. And the positive feedback will flip in. So inverter state will be lost. Or the SRAM will lose its data. Here, SRAM did not lose its data. You started with VDD, ended with also VDD. The yellow is this node, Q. And this dash line here is Q bar, which is VB. So VB remains same because your propagation delay was long. There can be some fluctuation, but this is not enough to change the steady state. So that is the very important aspect for SRAM. And in questions, right, there will be in homework 6, we have several questions based on different propagation delay and all those things. So all those concepts will come back. So let's look at the mathematical aspect of it. So your critical charge for SRAM is little complex. One is what is the initial charge plus what is the supplied charge. Supplied charge is your propagation delay times T on. So your initial charge, suppose it was Q equal to 1, CVDD, and that was more like your stored charge, right? For DRAM, for example, half CVDD was your critical charge, but here it is more actually. So it's difficult to upset an SRAM because your critical charge is not just stored charge plus how much you can supply in this propagation delay time. Right? So to add that part. So this is important. And then you can see is your collected charge more than this or not. Okay, so this is your large propagation delay will prevent single event upset because large propagation delay will also increase your critical charge. So critical charge is not as simple as just capacitance and voltage. It depends on the time and everything. Questions, comments, anything so far? So yeah, I'm talking about a lot of equations, a lot of stuff, but these are simple equation, right? This is Q equal to CV type equation, and hopefully this gives you an intuitive understanding of radiation effects on memory. So your if your collected charge is more than the critical charge minus the threshold charge, right? Threshold charge is like threshold voltage. You don't need to go from VDD to 0 to upset. If you go from VDD to some extent, right, like your noise margin in DRAM, you can cause upset. So this is the Q threshold. Q threshold is your threshold charge, which is more like capacitance times threshold voltage, roughly. So then you can see an upset. Okay, and you can see this is the voltage dynamics. So we talked about conceptual understanding. These are PowerPoint diagram, right? But if you look at actually how it happens, so you can see here you induce the current. So this spike is the radiation induced current spike inside the memory cell. Because of this, your 1, right? This is your Q equal to 1 and this is Q bar equal to 0. So Q equal to 1 goes down, but it restores because your propagation delay was good enough to restore this lost charge. But here, this is the current, but if your propagation delay is less enough or critical charge is less enough, it goes down, it tries to go back, but it could not, and then it goes. So this is the flip. This is where you'll see upset in SRAM. In this case, even though there was some disturb, but it did not cause upset. So this time dynamics is very important in DRAM, sorry, in SRAM, right? But for DRAM, I think there is no one to rescue. So refresh, yes, you can increase the refresh interval, but typically it is carefully designed. So the refresh interval is also power hungry, right? You have to refresh means your power dissipation goes up. So you should see more soft error for DRAM for the same size. Questions? So one big message from SRAM you got that, okay, propagation delay of in the inverter matters. Longer propagation delay is better. Suppose you have a SRAM which is having smaller delay, right? You designed it. How to increase this propagation delay?
There are wires.
Yeah, you can play with those resistances of wires, and also in one aspect, you can just make it more resistive. Those wires you can make more resistive, which is bad for typical operation or usual operation, but for space application, maybe we can compromise with some delay. Right? You can intentionally make some of those SRAM cell more delay, and that can cause radiation hardening of the bits. Just one simple example. Okay, so this is what we learned so far in SRAM, that radiation dynamics is far more complex than DRAM in SRAM because there are multiple junctions sitting around. So you need to look at which junctions are more critical connected to this storage node, right? So there's one. And the timing aspect of the inverter or inverter delay plays a big role for critical charge determination. It is not this initial charge, how much charge you stored. It is how much charge you can restore as well during this propagation delay time. That can decide whether cell will cause upset or not, right? For example, here, upset took place in this particular case. So let's look at one problem and then we'll be pretty much done. So typically SRAM cell capacitance is much low, but in this case 100 femtofarad. Your supply voltage is 1.2 volt, threshold voltage is 2.2 volt. These are the parameters given. Within this parameter, you have to see whether a strike can cause upset or not. So your alpha particle emitted, right? Alpha particle can be from a packaging material also, right? Your ceramic that you do for package your chip, that can also emit sometimes alpha particle, given that it has some radioactive element inside, right? So as I said at the beginning, this issue was first observed in 1970s in DRAM, where it was done in Colorado. Some mine water was contaminated with some radioactive material. Very tiny fraction is good enough to cause upset. Okay, so now, just after particle strike, find the voltages at Q and Q bar, this is one, and you're assuming alpha particle deposits 0.2 coulomb, right? By striking the drain of N1. That means here. Here the strike happens. At Q, we'll see dip in voltage. It is in hold state. Everything is closed out. You can word line is 0, bit line is 0 because it is holding the data. But and you want to see whether a silent data corruption has happened or not. Silent data corruption means it is undetectable, right? Pass through it. You don't know. You have not written or you have not done anything. Suddenly you will see bit flip. Right? So question is whether this strike can upset the bit. So we'll again move on with the same charge calculation. Q equal to CV. This is the only equation we are using in this discussion. Okay. So propagation delay, for two different propagation delay you have to repeat. So first one is 1 nanosecond is your propagation delay, and the second one is 2 nanoseconds. Second one will be more resilient to radiation, upset, because propagation delay is long. So let's first see whether. So first you find out what is the deposited charge and what is the corresponding change in voltage, right? Because the first part is just after strike, what is the voltage? So Q deposited is -2 picocoulomb because NMOS was striked. So negative charge will be deposited. Okay. So delta VQ is Q deposited by this. So -2 volt will be dropped. That means after just strike, or 1.2 volt will become -0.8 volt. So that is your instantaneous voltage just after strike. Right. So just after strike, Q bar, what are the voltages at Q bar? Before strike, Q was 1.2. So Q and Q bar, right? These are the two floating node in SRAM. Before strike, this was 1.2 volt, this was 0 volt. After strike, what are the voltages?
Q bar doesn't change.
Q bar doesn't change, that's correct. So that will remain 0 volt. This will become -0.8 volt. -8 volt. Now thing is, it's still not upset. This is restoring as well. Upset means this should be, if upset happens, steady state voltage will be, this will be 2 volts, so 1.2 volt, and this will be 0 volt. This is your steady state. If upset happens. If upset. If no upset, then what will be steady state voltage? It will be exactly the same. Right? If no upset. Makes sense? So we have to find out what is the steady state voltage. So we have to see whether upset happens or not. And that's why you have to do this Q collected and Q critical comparison. Okay, so let's look at what is the critical charge. So the final charge at this node Q after 1 nanosecond, right? So after 1 nanosecond, you have to add the PMOS will supply, right? Because this node is at negative voltage, right? The PMOS, corresponding PMOS will keep charging that capacitor. So Q supplied is PMOS current, on current of the PMOS, because that P1 is on. If you look at here, this PMOS, right, is on. This is 1, this is off, this is on. So the moment this voltage went down to negative, immediately VDD, right? Supply voltage 1.2 will keep charging it. So this is the charge we are collecting here. On current of the PMOS times propagation delay, and then your initial charge was 1.2 picocoulomb. You deposited minus this, so this was your total charge. I think this picocoulomb. So corresponding node voltage will be 0.1 volt, which is low enough to cause upset. This is the final voltage, right, after your propagation delay. So this is 0.1 volt, which is lower than the threshold voltage of the transistor. So that means after the strike, there will be an upset. Questions? Okay, so this upset happens means your steady state voltage will be 0 and 1.2 volt. Your instantaneous voltage is this one, -0.8 volt and 0 volt. Okay, so I think that's pretty much the thing. You can. So there will be, you can repeat this for t propagation 2 nanosecond. At 2 nanosecond, you will see there is no upset because longer time. So this current will increase. Instead of 1 nanosecond, this will be 2 nanosecond. So this charge will make final charge on this capacitor high enough so that it is not below the threshold voltage of the MOSFET. Yes.
So would having a higher VDD make
Helps.
it more tolerant?
Yeah, absolutely. So if you design a MOSFET with, but yeah, all those things has penalty, right? Because high VDD will cause power dissipation. Your static power dissipation depends on leakage current times VDD. So that's why during hold operation, you typically lower down the VDD. Suppose you have designed it for 1.2 volt, but you can, for minimize power dissipations in space, right? Power is critical. You have to lower down the VDD. You have to make it 0.6, 0.7, that even it will be more susceptible to upset. Any more questions? Those are important, right? If you think about from a system engineer, suppose you want to work, right? So now you have to do this dynamically. Hold voltage, what hold voltage you want to go. So these are the critical criteria, because during hold condition, if a bit got upset, you never noticed. This is called silent data corruption. Suddenly you'll see data doesn't make sense, or your SRAM FPGA is having a different configuration file. So yeah, those are critical for understanding soft error. Now, typically it is measured or quantified in the form of cross-section, right? So cross-section means you have a chip, some ions are going in, number of ions is quantified with fluence. Fluence means how many ions crossing per centimeter square, right? Whatever ions, suppose you want to do a testing, then you know the beam has this many ions passing through, right? Or if you think about a space, you know that, okay, if I wait for a day, this many ions will pass through it on an average in a particular cross-section area. Now, sensitive area, which is that per bit, right? How many bits got upset. So if you define this cross-section for memory die, it is more like N is the number of errors that you observed, and F is the fluence of the beam. Fluence means how many ions are passing by per centimeter square. Not all will cause upset. So yeah, so N divided by F will give you cross-section unit as centimeter square per bit. That means for 1 bit, what is the cross-section, right? Or for 1 bit upset. So that is the typical way of quantifying soft error rate in terms of cross-section. Okay. So higher cross-section is good or lower cross-section is very good? Lower cross-section is good because higher means more probability as chip will be seeing an upset. So this is a failure area. You want failure cross-section should be as small as possible. Right? Or higher cross-section means your N is large, so fail bit is large. So that's why Y-axis is the cross-section, centimeter square per bit. This is measured data on SRAM, and X-axis is the LET of the ions. So there's a critical LET. After this, you can see your cross-section is going up. That means failures are happening, and then there will be a saturation cross-section. After that, basically enough LET. If you change the LET, LET means your energy of the ion. If you're increasing, you have a higher chance for upset. Okay, so this is a typical way of measuring this soft error rate. When you test a chip, you basically plot these kind of things. You find out what is the critical LET. For example, if you have a red hard process, you should have critical LET, means LET at which you see failure is happening. That means critical charge condition is achieved, right? And then there is some probability it will saturate after some time, but there is a range. So you can say what is the critical LET and what is your critical cross section. These are the two important. So what is the saturated cross section, sigma set, and critical LET. These are the two important parameters to quantify soft error or single event upset